Welcome to the demonstration of our robot-assisted precision drilling system. In this project we are performing collaborative drilling tasks on a curved workpiece using a robot and an augmented reality interface. Here you can see the experimental setup of our project. As you can see, our collaborative robot, Cobot, is an LBR iiwa 7 model from KUKA company. This robot is able to move in three-dimensional space with 6 degrees of freedom. The workpiece you can see here is a curved plywood part, belonging to the backrest of a wooden chair. We aim to drill multiple holes at different locations and different drilling angles on a curved surface. It is very challenging to manually align a drill to the desired angle at a determined point for drilling. For this reason, we seek assistance from a collaborative robot and an augmented reality interface. Visual markers are placed on the workpiece and tracked by the AR goggle. Here we can see a drill setup attached to the end effector of the robot. There are also 2 force sensors connected to the setup. One of the sensors measures the interaction force applied to the robot, while the other measures the force applied by the human operator. In this system, we use an admittance controller with 6 degrees of freedom, which converts the interaction force applied to the robot into a reference velocity, which is then followed by the internal controller of the robot. It can be hard to remember the sequence of the drilling target points in a real manufacturing environment, as well as how the operator should approach those points when the number of drill targets increases. To this end, we are using a Microsoft HoloLens goggle. The difference between this device and regular spectacles is that it can place virtual objects and scenes on top of the actual scene observed by the wearer. In this demonstration, the local surface normal is derived with any of our surface normal detection algorithms pHRI. Therefore, the positions and drilling angles of all the target points on the curved surface are already registered in the system. A transparent red hemisphere is displayed on the drill target, as well as a transparent white vector pointing towards the target, aligned with the desired drilling angle. It is therefore sufficient for the operator to bring the robot to the vicinity of the drill target where the hemisphere is located, while roughly aligning it with the white vector. Once the drill tip makes contact with the virtual hemisphere, the robot aligns itself exactly to the desired drilling angle. At this stage, all the operator has to do is to push the robot, and thus the drill towards the target point, to commence drilling. The adaptive admittance controller is transparent during free movement, so as to follow the operator's intended motion. However, during the drilling process, it is more rigid, thereby preventing instability and damage to the operator. Now we will see the operator, comfortably and precisely, opens 2 other holes on the workpiece with specific polar and azimuth drilling angles thanks to our haptic guidance, which fuses human intelligence and decision-making capabilities with robot's precision and robustness. To assess the efficacy of the proposed pHRI system, we have designed 2 sets of experiments. In the first experiment, we aim to examine a few quantitative metrics such as total task completion time, human effort, flexor carpi muscle activation and presence and absence of haptic guidance in a full drilling scenario using 3 novice subjects. In condition 1, the auto alignment and haptic guidance were active while the visual feedback to the user through HoloLens was only for indicating the target point. On the other hand, in condition 2, the haptic guidance was not active and the operator conducted the drilling with 3 different desired angles of attack, orienting the drill manually using the visual guidance provided through the AR interface. As you can see in the results, all the metrics are improved in favor of the presence of haptic guidance. In the second experiment, we invited 3 industrial workers with extensive experience in drilling and other small batch manufacturing processes to test our setup by drilling 3 holes on the curved backrest of a chair. Then we asked them to fill out a questionnaire asking for their subjective thoughts on different aspects of the proposed pHRI system. The 32 questions were arranged as shuffled opposing pairs with a 7-scale Likert score. As you can see in the results, most of the scores are higher than 5 out of 7, suggesting that the workers had a positive attitude toward the system. Thank you for watching.